In this unit, we're going to study medians and altitudes. Before we start, I want us to recall in the previous couple of units, we paid a lot of attention to angles. We studied various things like angle bisector theorems. That's all where we study the angles and then derived the relationship between angles and the sides of triangles. In this unit, we're only paying attention to medians and altitudes, which are lines. They're not angles anymore. So let's start with some definition here. Median of a triangle, it's somewhat intuitive. Look at my example here. I highlighted the point M, which is the midpoint. And if you connect vertex B with the midpoint M, my red line BM is my median. So in other words, median is the segment between one of the vertex and the midpoint on the opposite sides. And obviously I have three medians in this triangle, and where they meet is called the centroid. Okay? Altitudes are intuitive. When we climb a mountain, we know what altitude means. But when it's applied in a triangle, we're talking about we start from any of these three vertexes, you drop straight down and form a right angle right there. BL is my altitude. And again, because I have three angles, ABC, I can draw three altitudes, and where they meet is called orthocenter. Now let's look at how we use them. Concurrency of medians of a triangle. What this theorem tells us is that when I have DEF as the midpoint of the three sides in the triangle ABC, I can end up finding three medians, AE, BF, and CD. And notice that AP is 2/3 of AE, and BP is 2/3 of BF, and CP is 2/3 of CD. So in other words, the medians intersect at 2/3 of the distance from each of the three vertices. Now let's look at example 1. In this triangle FGH, M is the centroid, and we're asked to GM, we're given GM, which is right here. This is 6, and we're asked to find ML, which is the blue part here, and GL, which is GM plus ML, right? So we need to find ML first, it looks like. Maybe not. So let's see how we start with this. We know that because it's given that M is the centroid, so GM is 2/3 of GL. And we also were given that GM is 6, so it's just substitute that. We would have 6 equals 2/3 of GL. There we substituted 6 for GM. And if we do a little bit of algebra and we multiply the reciprocal of 2/3, we should end up having GL equals 9. Now, if GL equals 9 and GM is 6, obviously GL minus GM would give me ML, which is what I want. So I should have 9 minus 6, and that's 3 as my answer. So to conclude, my ML is 3, and my GL is 12, and my GM as given is 6. Okay? So the math part, the calculation part is almost non-existent. It's all about seeing that the centroid M and GM has to be 2/3 of GL using the concurrency of medians of a triangle. Let's look at this example. It says the vertices of this triangle JKL are given. So J is at 1, 2, which is here. That's J. And K is at 4, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 is here. So 4, 6 is my K here. And L is at 7. 7 is here. 7, 4. 1, 2, 3, 4. Does that look right? I think that looks about right. It's not precise, but it looks about right. So here is my oops, sorry. Let's erase that. And here's my triangle. Not so elegant triangle. There we go, a little better. Oops. I swear that I'm so glad that your art teacher is not seeing this. This is just such lousy drawing, isn't it? But you got the point. That's my JKL right there. So what are we asked to find? We're asked to find the coordinates of the centroid P. So P is not given. The P would be, if I use a different color, P, I would say it looks like it's going to be somewhere here, around here. I don't know exactly where. So I can use any of these points, the coordinates, to find the midpoint of the three sides. But I probably should pick a side that's easier for me. Let's see. The solution here says it's asking us to sketch that. We did that. And it's asking us to find the midpoint of JL, which is right here. It should be somewhere here, the midpoint M. And obviously to find the midpoint, we talked about finding midpoint is like finding averages. So all we need to do is to add the x coordinates of J and L together, which is 1 and 7. And then add the y coordinates together, which is 4 and 2, and then divide them by half. And in which case we now end up with M should be at 4, 3. Did I do that right? 4, actually it's about right. It's right here. That's my midpoint. Once I have my midpoint, I can connect my vertex with my vertex K with my M, and then I find the 2/3 point. I should find my P, right? That's because the centroid is at 2/3 of the distance from each of the vertex to the midpoint of the opposite side. So the distance from vertex K to M is 6, which is right here. 6 minus, we said the midpoint is 4, 3, and K is 4, 6. And because they both are on, both have x value of 4, that makes it a lot easier. So to calculate the distance is really just 6 minus 3, which should be 3 units left. So then if I take 2/3 of that, I should have final answer as 2 units down from K to KM. So the coordinates of P would be 4 and 6 minus 2, so I should have 4, 4 as my, so 4, 1, 2, 3, 4. So here's my, here's my P right here. Should be somewhere there. Okay, I apologize for the lousy graph, but you got the point. The point is that you first find the midpoint on JL, and then because we're lucky enough that K and M are having the same x values, so then it's much easier for me to find the whole distance of KM, which is just 3 minus 1, which gives me 2. And then from there on, in order to find P, I use the total length, the 6 right here, this 6 here, minus that 2 units I just found. So that's how I end up with the y coordinates for P is 4. Here's another theorem, and this time is about concurrency of altitudes. Remember, altitudes is the segment from one vertex goes straight down to the opposite side and perpendicular to forms a segment that's perpendicular to the opposite side. That's our altitude, right? So this theorem says the lines containing the altitudes of a triangle are congruent. In other words, in this diagram here, CE, BD, and GF, these three lines are all congruent to each other. And of course, they meet at A. Actually, this is a mistake here. They meet at A right here. I think what the book did was that they reversed A and G. Anyway, so let's look at the example here. It says find the orthocenter P in the triangle, and obviously in this one I'm going to label it A, B, C. This one I already have one, and this one is just this one, and then the third one, it should be I'll label that as D. So the orthocenter is B, okay? And for the next one, I would do, if I go from A, B, C. If I go, I guess this is asking me to graph it here. So I'm going to pick an easier one. This one, if I go to the other side, that's a straight angle right there. I should add the straight angle. That's a perpendicular line right there. And then notice this one is a little harder because this angle here is obtuse. So if I draw a perpendicular line to the other side, I have to go from this point, I have to go this way, I think. Right? That's where I am. And then the third one, I have to extend this a little bit, and this is my right angle there. Now you see that it looks like it's not meeting each other, and you can't help but ask the question, is our theorem correct? But look, if I just extend this line, then I extend this blue line, and then if I extend the bottom one, they do meet. The three altitudes do meet. They meet at this point D right here. And that's outside the original triangle, but they do meet, right? So that's a very interesting case for to find the orthocenter of a obtuse triangle. Here's an interesting question. It's asking us to prove a property of isosceles triangle. I cannot say that word, isosceles. It says that prove that the altitude to the base of an isosceles triangle is a median. So in other words, what we know, or what's given, is that AB and CB are congruent. We also know that this angle BDA and BDC are right angles because that's the altitude. And we're asked to prove whether AD is congruent to DC or not, if they're of equal length. So notice that the angle ADB, here we go, whoops, sorry, angle ADB and the angle CDB are congruent right angles, right? Because BD is perpendicular to AC because it's the altitude to AC. Also, BD is congruent to BD, and we're given that AB and BC are congruent. Therefore, the two triangles ADB and CDB are congruent because of the HL congruence theorem. Now, if the two triangles are congruent, all of its corresponding sides and angles has to be congruent, and that's how we know that AD and CD are congruent, right? So that's CPCTC. So because of that, we can draw the conclusion that D is the midpoint of the side AC, and therefore BD intersect AC at its midpoint, and BD is the median of triangle ABC. So that's how we prove that the altitude to the base of an isosceles triangle is also a median. Okay, so this only happens with isosceles triangles. If the angles are not, if it's a right angle that's not isosceles, or obtuse triangle, this will not happen. The altitude and the medians are independent of each other. Okay, thank you guys.